that. So a lot of business trips are now becoming virtual trip, even after COVID, because companies want to save money. So yeah, they're saying there's going to be a lot of issues later on because of this. Even when the virus is done, it just changed the dynamics. Lives that it's not just easily reversible.
Yeah, let's take the positives, drop the negatives.
Yep.
Let's be more social, etc.
True.
Well, maybe we can start by introducing our speaker, who very, very generously agreed as usual with his positive spirits.
Thank you.
I'm very happy to introduce Dr. Ali Matuk, who recently finished his PhD degree at Supélec in France. He obtained his master's degree also in CentraleSupélec in France. And in 2018, 19, and 20, he was a visiting PhD student at the University of Maryland, College Park in the US. And he has an interesting travel story trying to come back from the United States during the pandemic, I believe. He's the recipient of, I can't pronounce this, Labex Digicosme.
Yeah, that's it.
Scholarship for academic excellence in 2016. He's also recipient of both the regional and national André Blanc-Lapierre awards for best master's student in France in the domain of electricity, information technology, and communication. He's currently doing a postdoc at CentraleSupélec. His interests include massive MIMO, NOMA, which stands for non-orthogonal multiple access, and the age of information, to which he has contributed some of the pioneering works, especially new semantic metrics, starting with the age of incorrect information, as far as I know. Yep. So without much further delay, I leave the floor to Ali.
Thank you for the introduction, and good morning, everyone. So like Professor Alif said, my talk today is toward semantics and power communication paradigm, is based on the PhD work that I've done between CentraleSupélec and the University of Maryland. And my talk is going to be divided into several parts. First, I'm going to start and introduce the motivation and the problem that we investigated during our work. I'm going to go into details about the age of information, and I'm going to also to go beyond that and talk about the age of incorrect information, and then finishing up with a summary of the talk. Okay, let us start. So as Aristotle stated in his book, Politics, man is by nature a social animal, okay? And the basic building block of our social life is what we call communication. And communication is basically a process where you have a source that generates a certain message that goes through the channel, and then it arrives to the receiver, who then can decode it and understand its content. And because of how vital communication is to our lives, humans have been, since the dawn of humanity, trying to come up with new forms of communication, that would be the hieroglyphic, the alphabet, and all of that. Now, what's interesting is lately, communication is no longer exclusive to human. We talk about, sensors communicating with one another, and we talk about this famous, buzzword, the Internet of Things. And because of how important this machine-to-machine communication is to our lives, McKinsey, the consulting firm, estimates that by 2025, the economical impact of the Internet of Things is going to be from $2 to $6 trillion, and that just shows how important it is to our daily lives. Now, why do machines communicate? Well, basically, machines communicate to provide what we call real-time monitoring services. So what we have exactly, we have a source, that observes one or multiple processes. So, for example, this process can be, a temperature, humidity, velocity, whatever it is. And its goal is to inform a remote monitor about these processes. And the way it does that is by sending what we call status update packets. Basically, these are just packets that says, okay, at this time, the value of the process was equal to this. Okay. Now these packets can either be generated by the sensor at will. The sensor can decide whenever he wants to sample and just send this packet, or they can arrive stochastically without its control. So basically, we have this type of scenario. We have data samples or update packets. We can use these words interchangeably. They go through to the buffer of the source, and then they are sent through the channel, and they arrive to the monitor. This is the simplest scenario. Now, what's interesting is we can have a combination between the source and the receiver. So we can have, machine to machine, machine to human, human to machine. And the channel can be any combination of both wired or wireless links. Okay. Now, some examples for such services. We have robotics control, when we're trying to control a robot that's so far away. And, a simple example is the Mars Perseverance rover that's, been receiving a lot of buzz lately. And we have industrial monitoring where we could have, sensors that collect data of the plant and then forward them to a central controller, for analysis and stuff like that. Vehicular networks where, vehicles can communicate with one another to, exchange information about velocity, position, and maybe like traffic jams, stuff like that. And we have environmental monitoring where you could, put sensors in a certain area of interest and, gather data about the temperature, humidity, wind levels, stuff like that. Now, the most important question is, how do we optimize these networks? Like, how can we get the best performance out of them? Well, basically, we need to ask ourselves first, what is our goal in such networks? So first of all, based on what I just said, our goal is to make sure that the monitor is up to date on the process that is observed by this remote source. And we also need to keep in mind that the information has the highest value when it's fresh. What do I mean by that? Basically, suppose you have a buffer where you have two packets, one that tells you, the velocity of the vehicle a few seconds ago, and one that tells you what the velocity was like an hour ago. Of course, the one from a few seconds ago means much more to you than the one from a long time ago. Now, traditionally, when we had like networks, and we want to optimize, usually we adopt one of two approaches. We had, these are like the most celebrated ones. We have throughput maximization, which basically just tells the source, okay, you need to send as much data as you can, okay? And what will happen then is like the source will generate a lot of packets, trying to maximize its usage of the channel and all of the resources. But what's going to happen because of that is there will be a lot of congestion in the network and a lot of queuing delays. So basically, because of this, the monitor actually will end up having, not being up to date because the packets arrive really late to the monitor. Now, there's another approach, it's delay minimization, which basically just says, okay, we just need to make sure that the time that the packet needs to go from, one end of the network from the source to the destination, the monitor, is minimized. Now, what's going to happen is the source will try to decrease the generation rate of packets because it wants to avoid congestion and queuing delay and stuff like that. And this has been discussed a lot, especially in InfoComm 2019, where some people said, and it just puts it really clearly here, is that there's no delay if there's no transmission. So we can see from both these frameworks do not work in achieving the goal that we have. So the question is, why is that? Well, the reason behind that is because these approaches go under the umbrella of what we call context-blind approach. What do I mean by that? It means that they do not consider, when doing the transmission decision, how much information a packet can bring to the destination. So basically, packets are treated equally when transmitting. So let me go back to the example I just gave a little bit ago. When I had these two packets, one that tells me the velocity of the vehicle, a few seconds ago, and the one that tells me what it was an hour ago. From the perspective of these two frameworks, these packets are equal, but we know that this is not the case. And this is an issue with traditional communication paradigm because we have this blind approach to data packets. We don't look at how much information they could bring. And there's this separation between how you acquire data and how do you use these resources. So what's the solution to this? Well, the solution is to incorporate what we call semantics of data. And the word semantics here means significance. And basically what we mean is when you try to transmit, you take into account how useful this package you want to transmit into a certain communication goal. And one of those semantics of data, approaches will lead to what we call the age of information metric. So what is the age of information? So the age of information was introduced in 2012. And what it does, it captures one aspect of semantics, which is information freshness, which means that whenever I try to transmit a packet, I look at how much this packet is important to achieve a certain information freshness at the moment. So to understand that, let us take just a simple example. We have a packet or a sample I that is generated at time Si. And of course, there's delays in the channel and stuff like that. So it is delivered at time Di. The age of information is basically the difference between the current time and the generation time of the last received packet by the monitor. So for example, we can see here that, as long as the monitor is not receiving new packets, the age will grow because, the monitor is not receiving anything new. And once a packet is delivered, the monitor gets new information. Those will lead to a certain drop in the age of information. And we can see from this, expression here, when the age is small, that means the monitor is up to date. And when the age is really high, it means that the monitor hasn't received a packet about the process in so long. Now, using this age process, we can define what we call age-based freshness metrics. We can try to say, okay, we are interested in, minimizing, we try to minimize some metrics to achieve this information freshness. We can say, we can try to minimize the time average age. We can say we can minimize that average peak age, which we, trying to minimize these peaks right here, the average of these peaks. We can try to minimize a certain non-decreasing function of the age. And this has been done a lot in the literature. So there have been a lot of work where, we try to optimize age-based freshness metric and queuing system. We try to find expression of these age metrics. We try to some people showed that the last generated first serve queuing discipline is optimal in multi-hop networks. There have been a lot of proposition of optimal sampling policies to minimize the age for delay channels. And also age was incorporated in scheduling decision, when you try to decide which user gets the channel. So there have been age optimization in broadcast networks, and there's been scheduling in single and multi-server systems. So there have been a lot of literature work on the age metrics that I just talked about. And people even went beyond that, and they said, let's see if there's some relationship between the age and more fundamental metrics. So they were able to show that the error is actually a function of the age when you take samples, you don't look at the information process. And when you have a plant and a controller that are governed by a linear time invariant system dynamics. But in general, they were able to show that just because you maximize the freshness or minimize age doesn't mean you are having the best error performance. So as you can see, there have been a lot of research efforts in this direction. Now, what's the issue with the age? If I ask you what's your first impression about where it can fall short, well, basically the problem with the age is it does not consider what the monitor knows. So I can give you an example. If you have a sensor in a certain room, okay, and this sensor is trying to gather temperature data of that room and relaying it to maybe your smartphone or whatever it is, a remote monitor. Suppose you have this information, you know that the temperature is equal to 20 degrees Celsius at this instant. Just because you haven't received information from the sensor in so long, doesn't mean you are doing something wrong, because maybe the temperature did not change. So that's the issue with the age, is it penalizes you even when, you know, just as long as you're not receiving information, you are being penalized. So what that will lead to, it will lead to wasting resources on unnecessary updates, because, you know, if you want to minimize the age, you will have to send packets, even though like the monitor, you know, may have perfect information right now. So that's the issue with the age. So researchers said, okay, then the way we can deal with this is try to take an error approach. You know, we try to define a process at the transmitter x of t, and we consider that the estimate at the receiver is x hat of t. And we just consider x hat of t equal x or u of t, where ut is the timestamp of the last received packet, which basically just means I'll just trust whatever last packet that I get. I'll just take it as the value of the process right now. And what you could do in an error approach is you try to make x hat of t and xt coincide by minimizing one of these three metrics. You know, you have the indicator function here. So by minimizing this, you minimize the prediction error. The average of this, you'll minimize the prediction error. If you minimize the average of this metric here, you get the, you know, the minimum mean squared error. So that's what you know, researchers tried to do instead, you know, of the age. That's like an alternative to the age. Now, what's the issue with the error approach? Well, first of all, we need to keep in mind that perfect data replication is not possible in a realistic scenario. You're gonna always have delays. You're gonna always have, you know, maybe like channel errors, stuff like that. So realistically, you cannot have this perfect data replication at each time instant between xt and x hat of t. Because of this phenomena here, it will put into perspective a certain shortcoming of the error. Basically, the error metrics do not take into account what is, you know, how this x hat of t is used, you know, what is the application of x hat of t. So basically, it does not take into account what does the mismatch between x hat of t and x of t has on the system's performance overall. The best way to understand this is to take this simple example. Suppose you have two bursts of errors. You know, you have one error of time duration 1 and another error of time duration 1. And you have a longer error of duration, you know, 2 times less. From an error perspective, these two are equivalent. But we know there is a lot of application where this case here is worse because the error took longer to be resolved. So this is the issue with the error, and to understand it more, let us just take this simple example. For example, suppose the process that we care about is xt that can have 2 values, 0 or 1, where xt, you know, is if the machine that is being monitored by the sensor is at normal temperature, and it's equal to 1 when the machine is overheating. So basically, why do we send packets to the monitor? Is because to make sure we achieve a certain goal, which is turning off the overheating machine as quickly as possible. Now, we know that as the longer a machine is overheating, the higher the chance for it to break. And that we know from, you know, physical properties of whatever in the machine. And so if the effect of wrong temperature data after 5 seconds is definitely not the same after, like, for example, like 60 seconds. So basically, to summarize, the age of information will waste resources on unnecessary updates because it doesn't take into account what the monitor knows, and the error penalty does not capture, you know, the deteriorating effect of the wrong information on the system's performance. So that's when we sat down and we said, okay, let's try to overcome these shortcomings and try to propose a new metric to deal with those problems. And that's when we came up with the notion of age of incorrect information. So let me just rewind a little bit. So what do we want from this metric? We want to make sure this metric take into account the information content of the updates and what the receiver or the monitor knows. And it should capture the deteriorating effect of the wrong information on the performance of the system. So the age of incorrect information is basically a multiplication between 2 metrics. We have a time penalty function here and an information penalty function here. To understand it, I'm going to give a few examples right now of these functions. For example, let's just take this simplest one. We just take the function, the time penalty function as t minus vt, where vt is the last time instant where the monitor was in a correct state. Now, given that, let's just think about the exponential one. The exponential time penalty function is exponential a t minus vt. Basically, what does that mean? It means that when I do not have correct information, the penalty of my system just grows really high. It just explodes. But for example, we can adopt another time penalty function. It could be, for example, an indicator t minus vt is larger than a certain threshold. What that means is, like, for a certain time threshold, I'm okay with having bad information. I can deal with that. But after that time, no, like, you need to give me correct information. And the example of G, we can have just the same stuff that we had from the error approach. The indicator, the squared, error, that's just examples. So to understand even more, let's just take an illustration right here. Suppose you have a two-state information source, xt, x can either be equal to 1 or 2. And let's just take this small example of age of incorrect information where f is linear and g is the indicator function. You can see here, if you adopt the metric age, what's going to happen, even if you know exactly if xt is equal to x hat, you are still being penalized. And that's the issue that I talked about with the age. We saw that this is not the case here, which is good. But the problem is with the error here is that it's always kept to a constant. You're always penalized the same way, no matter how long this T1 and T2 could be. For our case here, no, we are penalized more, the longer this interval of time where you're in an error is. Okay, so with that in mind, now we can understand the metric. Let's try to analyze it and see how it works. And and to do that, we just consider a simple scenario where we have a slotted time system where slots are just normalized to the slot duration, which basically just means that time is equal 1, 2, 3, 4. We have an n-state discrete time Markov chain. So this is the information process that the source is observing, such that you can stay at the same state with a probability PR, and you can transition to another state, with probability PT here, PT, to any of the others. And we suppose that transmission between the source and the receiver takes one slot and succeeds with a certain probability PS. And of course, if a transmission fails, you can always try to generate new update packets. So you have this ability to generate these packets whenever you want. Now, the problem is we need to optimize this age of incorrect information. So we try to minimize the average of this age of incorrect information subject to a certain constraint. Now, first of all, we considered a set of scheduling policy or transmission policy that are causal. What I mean by causal is like you only have information about the history. You don't know anything what's going to happen in the future. And we suppose that psi here is equal to 1 if a transmission is attempted. So basically, this constraint tells us you cannot just send a packet whenever you want. You have a certain energy constraint or an update rate constraint. So you have something that's holding you back, if that makes sense. And basically, this problem, is modeled as a constrained Markov decision process. And usually, these problems are not easily solvable. So the question was, what is the best sampling / transmission / scheduling, whatever you want to call it, that minimize the average age of incorrect information? So we analyzed this problem and we're able to show that the optimal sampling policy is actually a randomized threshold policy such that you transmit a packet whenever the age of incorrect information is larger or equal to n1 star. You do that with a probability rho. And you transmit what's larger or equal to n2 star with a probability 1 minus rho. And an here is just the update rate for a threshold n, and rho is chosen such that the update rate is equal to alpha. There's a lot of math here involved, but basically we can show that this is the optimal policy for us here. And how do you find this N1 star? Where we're able to show that there's a binary search algorithm that finds this threshold for you. Also, in one of our recent work, we generalized this to more general functions, so not just the linear function that I just adopted here. We went even beyond that to any more general function f and got similar results. So now that we have the optimal policy, let's try to compare it with the age optimal policy and the error optimal policy so we understand its merits. So first of all, let's suppose, you have n equal 8, ps equals 0.8, and pr equals 0.5, just like some fixed parameters. We can see that no matter what the alpha is, just to recall, the alpha is the maximum update rate here. No matter what alpha is, our policy always achieves the best average age of incorrect information. And we can see that the performance between the two coincide as alpha tends to 1. And the reason behind that is when there's nothing holding you back, alpha is equal to 1, it means there's nothing holding you back. What you just do is just transmit at each time slot. That's true for age, for error, for everything. So we also try to compare the two in terms of average age, and we can see that the average age policy for sure is better than us in terms of average age. And we can also note that the gap between the two curves is the largest for low alpha. And the reason behind that is when you are constrained with resources, your decision matters even more. So this is why, the gap between the two are the largest when alpha is really small. It means there's a lot of constraint on you. You cannot update a lot. Okay. Now we said, let's just fix alpha and try to, change the parameters of the information source and see what change. So in this case, we fix alpha to 0.1. And we're able to see that as PR is higher, as it increases, the gap between the two curves increase. So why is that? Because when you have high PR, there's less changes in the process. I'm just going to go back here. You can see that there's a higher probability that you stay in the same state. So basically, you have less chances of, of changes. So basically, what happened is the age of information does not take that into account. So that would lead to a lot of waste of resources. And this is something we talked about because the age of information does not, take into account that, okay, maybe the monitor now knows exactly what the process is. So then we said, okay, now let's try to compare with the error metric. So we took some settings, we took these values here. And the error optimal policy is basically just to send a packet whenever xt is different than x half t in a way that the update rate is constrained is verified with equality. And we were able to show also that, our policy achieved the best average of incorrect information, age of incorrect information. And we can see that the gap between the two decreases with alpha for the same reason as I said for the age one, because when you relax alpha, when alpha is high, nothing holding you back, you just transmit at each time slot. Okay, so that's, we understood how it compares with the age of information and the error. Then we said, let's see some real life application where we can use this metric. So we considered a real-time video stream packet. You have a source that's streaming a certain video and sending it to the monitor. And, the frames of this video are just a one-dimensional vector of length m. And we consider that we have a slotted time system that's normalized to slot duration, and the t is the video stream duration. We suppose that between the source and the monitor, there's a certain channel, xt, and the source always keeps an estimate of this channel that we denote by x hat of t. And we suppose that the channel is just a simple two possible values. You can only have two possible values. And such as the probability to stay in the same channel state is PR, and the probability to change to another channel state is PT. And we suppose that transmission error occurs when the estimate of your channel is different than what the channel actually is. So what the source can do is learn the channel using some pilot signal or stuff like that at the beginning of the time slot, which succeeds with a certain probability. But you cannot just train whenever you want. the training incurs a certain cost, and there's a constraint on how much on average you can incur of this cost. So what's the communication goal here? We go back to the communication goal. The communication goal between the source and the receiver is to make sure to the video distortion minimized by trying to like train and sending those pilot signals and learning the channel. So it turns out that the total video distortion is actually the sum of some separate distortions, and where each one is just the time of the error between the channel and the estimate. And turns out that the total average distortion is just a special case of the average of the age of incorrect information, where you have f of t is equal to this function here, and g of t is equal to this function here, where alpha, c, and d are just specific parameter of the video. So if we plot the three policies, the age optimal, the age of incorrect information optimal, and the prediction error optimal policy, for this specific scenario, this t equal 10 to the power 6, alpha 0 equals 6, c equal 2, and d equals 17, we can see that the average of incorrect information, age of incorrect information, achieves the best video distortion. So it's the minimum video distortion. And also we can see that the gap between them decreases when the power budget ratio is high. For the same reason that I've talked about. It's basically because when there's not a lot of nothing constraining you, you just try to train for the channel at each time slot. And that's it. So that's like part of what we've done during the thesis. And just to conclude, so we talked about the semantics of data, and we established a certain performance metric for status update system that takes into account this communication goal. We provided an optimal sampling policy and compared it to the age of information and the status error frameworks. Now, as for future research directions, there's a lot of things to be done. So, for example, for the age of incorrect information, generalization for larger family of functions. So this is something we've done lately, but we haven't done for G, for example. We only consider discrete time system. There's continuous time system as well, and it's always better to put more real life application. And in our most recent paper, we gave like many real life application besides this video distortion one. And for more general research direction, there's a lot of work on age of information, like physical layer solution. For example, MIMO beamforming. And of course, this notion of semantics of data is still not 100% concrete. There's a lot of work to be done in that area too. So thank you for your time. And these are the references that I've put in during the presentation. If you have any question, please just let me know.
Thanks a lot, Adi. That's really interesting. A very new field, as I try to say in the bio of the speaker. Of course, I'm familiar with it. I'm sort of working in the area, so that's why I'm partial to it. But I hope those of you who are in different fields also found something to take away. Well, I mean, we are all in one way or another involved with IoT. And the new Internet of Everything paradigm. So good to know that how the communication research is sort of changing.
True.
Well, I personally have a couple questions, unless anybody has questions. So basically, one of my questions is, in your result about age adaptive versus age of incorrect or information adaptive, with alpha not being a constraint. There, you do not consider the effect of delays in the network.
Exactly.
Yeah. I don't remember. Maybe I should have. I'm being ignorant, perhaps. But in your other work, have you considered delays?
So in terms of age of incorrect information, so my work, no, but there's some work with Professor Efremides and the people at NRL. did some recent work. I think it was just last year, where they consider, retransmission. So for me, I don't delay, because if you send a packet and it doesn't work out, you just generate a new one. For them, no, you just keep trying. There's retransmission, so just like delay. And they studied the system right there. But I personally, I didn't work on that yet. Maybe in the future, we'll see. But for sure, there's a lot of things that changes when you have delay versus when you have this control.
Yeah, if you want to publish a couple more papers readily, you could add delay, because then you would not only be adapting to the changes in the source statistic, but you would be adapting, the source, but you would be also adapting to the channel. So definitely that would get you slightly different policies.
For sure, that's true.
I have another sort of a silly question. To me, it's like the correct information is aging. Right. Okay. So age of incorrect information seems to be double negative to me. Okay. What do you think about that?
Okay, I see what you mean. So for me, it's like when we actually had, it's funny because I still remember that I sat down with the professors and we sat down, I think 2019, when we were about to publish, and we're like, what are we gonna name it? And basically what we come up with is when you have incorrect information, that's when you're, penalized, and it's the age, how long it's been since the incorrect information. That's how we came up with it. But I understand that double negative thing, because it's it's the correct information that's aging, because the correct information is becoming obsolete somehow with time because of the transition and stuff like that. So I understand this point, but for us, we came up, let's just use that, and adopted that.
The video thing is very interesting. Do you have a work that is trying to convert that to a protocol?
Oh no, I didn't do that. So basically, in my last paper, it's right here. I think, where is it? I've put it here. It's on archive. We've put some application, and we took even more general distortion model. Here we took a specific distortion model. We were able to show that it's a special case where f is even a nonlinear function. So for here, because we only had linear, but it was actually a nonlinear function, but it all works still. And I didn't look in how the protocols work exactly, because I believe there's a lot of work in streaming and how they do a lot of calibration of
So in cloud gaming, for example, that's very important field at the moment. People are gaming in very high real-time mode. So there are some protocols that are built on UDP, application layer protocols that try to send the recent stuff and encode the important frames better, etc. So I guess your idea can be converted to a protocol like that. The thing is with video is you really want to, video is different. A video is for people, usually for gaming. Video in gaming is for people. But when it is really machine type real-time communication, the criteria change. So I think it's worth looking at, and maybe we can talk about it offline.
For sure. That's the thing, because in terms of protocol, I'm not, it's I do not have a lot of knowledge in that regards and how they do it and all of that. I think I've read, like you said, in terms of streaming, they use UDP, and there's a lot of calibration of how many packets you send and the window and stuff like that. That's what I understood. But I understand this could be somehow put into a certain protocol. So it's definitely worth looking at, sure. Especially being a gay, I love gaming too. I understand this cloud gaming thing, so it'll be even more interesting for me.
Okay, that would be nice. That would be finally a gamer doing something.
Exactly.
The theory, right? Okay, cool. Any other questions?
I have a question.
Yes.
Yeah, thank you, Ali, for this very nice presentation. I have two questions, actually. One of them might be a little bit still number 19, I think one slide before this one.
This one?
About this system model, which yeah. Does that go to a specific state? Because J here, to understand that, is it something like a birthday chain, or I don't know if the question is clear, because with probability PT, but I think the result should depend on how much does it change.
Sorry, can you repeat the question, because you were cutting off a little bit?
I guess. Can you?
I can hear you now.
Yeah. Yeah. So with probability, does that go to a specific state J, or with probability PT, is it the probability that the state changes and it can go to any other state? Okay.
So that's a good question. So basically, to make the math easy, to be honest, we have to take a certain symmetrical scenario where you can go with PT, with the same PT, to any of the other n-1 state. So that kind of like makes this look as like a 0-1 type of Markov chain. If you model it, you can probably transform it. But basically, this PT is the same to everybody, because we tried to see if PT is not the same when, you know, it's like P1, 2, if you go from state 1 to state 2. But the issue that happens there is like the mathematical model just becomes really difficult to analyze. You'll have to go to like relative value iteration or stuff like that to be able to solve it. But we just opted for like more simplest model where you can find the optimal policy easier and, you know, study it more. And yeah, just keep the more sophisticated model perhaps for another time.
I see. Thank you. I have 24.
24. Oh.
Then you compare the performance. Yeah. So I think you compare the performance with the policy that you send the packet whenever the status changes.
Mm-hmm.
Did you have a chance to compare it with a threshold policy on the state error? The threshold policy on X.
Well, you mean
Could you hear me? Sorry, I have a terrible Wi-Fi connection right
don't
now.
Don't worry about it. Don't worry about it. We're interpolating the words, so we're understanding to a certain extent. So just a question, if I'm not
mistaken. So I can write it down if you like.
If I understood correctly, you're asking whether he compared it with a threshold policy on the error XT minus XT hat.
That's the question, right? Yeah. Well, we didn't, because for us, we compared it just for the, sorry, let me just go here. Here, okay. So we only have an indicator, so we don't care about the difference. It's like these states for us, it's like A1, A2 is as bad as A1, A3. If that makes sense. We didn't consider, you know, A1 and A2, you know, is A1 minus A3 is like worse than A1 minus A2, if that makes sense. So if you go back to this model here, it's like the difference between the states doesn't matter on the system performance. Of course, why we took that? Because it's easier. It's much more simpler to analyze, because when we took into account like a certain difference between the states, then yeah, it just becomes a little bit more difficult to analyze. But I understand it has been brought up during our discussion. I still remember this, you know, this whole taking into account the difference also, not just whether it's equal or not, but also how far it is from each other.
Okay, thank you very much.
Thank you.
So in fact, maybe the difference is the more general case, and
exactly.
But it's hard. It's not tractable as much, especially for a lot of different processes.
Exactly.
In your case, your metric is sort of bypasses that.
True. With the indicator.
Yeah.
I think there have been some work with some other student, I think, who they are taking like more general ways, but of course it's like the math becomes more, you know, intricate. It becomes more elaborate. You'll have to like try to go to like more algorithms that, you know, take some time to solve the problem. They are not exactly like a threshold policy as easy as a threshold policy that I have here. You have to do relative value iteration and stuff like that to actually get what you want.
In a lot of cases, you may not need that detail, but
True.
it's worth checking this in control systems.
Exactly.
So that's another direction.
There's a lot of directions. Like there's only 24 hours in the day. So.
Yeah. Okay. Well, that's very interesting for us in general. Good. Thank you so much for giving this talk. Elif Tuğçe, who asked the question, is another new faculty member here. I don't know if you guys know each other.
Who is it?
Elif Tuğçe Ceren, who just asked the question. She's also a new faculty.
I've read her paper. I've never met her before, so it's nice meeting you. I've read because I believe she worked on the age before, right?
Yeah.
Yes. So I've read some of your papers and.
Yeah, the same for me.
Wait, I think this age optimal policy here. It's your paper, if I'm not mistaken.
Yeah, might be.
Yeah. I'm pretty sure that's your paper. I still remember, like, because I cited it. Yeah. So it's nice meeting you. So I've read your work. Now I know you personally. So
yeah.
Well, thanks a lot, Ali. Again, one day, hopefully, when the travel bans are lifted, we would like to host you here in person in Ankara.
Thank you. Hopefully soon. Hopefully we're done with this whole pandemic pretty soon.
Any other questions, guys? K1, would you like to say anything?
Actually, I haven't. I have an ignorant question, actually.
Yes.
Probably it's because of, well, the thing is that in age of information policies, the thing is, you say the system does not care, the system does not care that X and X hat are still the same thing. It still penalizes. But the problem here, we solve this problem with semantics in age of incorrect information policy. But what I cannot come up with is that nodes can be age aware. They can be age aware with feedback systems or whatever. But how can they be error aware? How do they know? How can they even have an idea about the difference between X and X hat? How can they be aware of the error function?
Okay, that's good.
Is it an estimation? Maybe that
it's just feedback. So basically, what's gonna happen is when you send a packet, okay, you get feedback that it got successfully delivered. So you know, for example, I sent a packet telling the monitor that the temperature is equal to 20 degrees Celsius, and I get a feedback that that the packet got successfully delivered. So now I always have in my mind that the monitor is going to trust this 20 degrees Celsius and is going to keep using that until I tell him otherwise. So that's how I keep track. So there's some feedback mechanism. Now, if I limit feedback and try to estimate, that's some interesting problems that, come up then. But for us, we have an instantaneous feedback. Everything's perfect. And that's how you can stay aware of the error and the difference between what you know and what the monitor knows.
And the scheduling decision is at the transmitter.
Exactly. So then when you take decision, you say, okay, so now the temperature is 21. And I know that the monitor the last time he gave me a feedback was 20. Should I sample or not? That's like one way to put it.
Okay, thanks.
Yeah.
Okay, done. If there are no other questions, perhaps we can thank our speaker. Well, thanks so much, Ali, for visiting us today.
Virtually visiting.
Yeah. It's good to see you.
Thank you for the invitation. I really appreciate it. And it's my
Sure,
pleasure.
we appreciate it that you made time. Take care and let's stay in touch.
Thank you. And hopefully I'll see you guys, when this whole thing is over.
Yes.
Okay.
Bye-bye.
Take care, guys. All right.